Okay, shall we resume? It's great that some of you have already asked questions right during the break. There's also, yeah, if you guys want a voice chat, that's fine. If you're remote and you cannot make the exam in class, make sure you let me know as a month earlier. Okay, make sure let me know. So we'll try to come up with a resolution. And also, there's this question about the ebook, right? I believe it's free as long as you are on the campus website, campus network, right? As long as you're, if you log in with a Cornell VPN, I believe that's free. Okay, great, very good questions. Okay, so let's begin the sort of second part of the lecture, right? This is the roadmap of the entire course. Like the course title suggested, right? We have two components, right? Two parts. So one is more on the digital logic, right? And the second part is on the computer organization. You guys will soon find out that actually the first few lectures should be fairly straightforward to understand. Okay? And things may become slightly more convoluted when we start introducing sequential logic. And in the second part, that's where we'll start building a real microprocessor. And also we'll make sure that you guys also build something on the FPGA board. So at the end, right, for lab 4, so you guys will build your own. Although it's simple, but it's going to be a complete microprocessor. Right. So here, let me try to answer the question I raised earlier. Right. So what exactly is computer engineering? Right? In fact, 2300 is the foundational course for computer engineering. The thing is, if you look at the digital computers, right? The things that all the gadgets that you guys are using and playing with. So those are our electronics devices, right? At the end of the day, right? So everything boils down to atomic physics, right? So it's really about the movement of the electrons and such, right? That governs everything. But the thing is, when you guys are running some software programs, you're writing Java or Python, right? Or even if writing some system software later on, like compilers, OS. OS means operating systems. You guys don't really need to worry about these are very low level details, right? So this again comes back to this notion of abstraction, right? Over here we have this so-called stack. So this is where we build up the layers and layers of abstraction, so that all these details are abstracted away from the software programmers, right? From the actual application users. You guys don't really need to worry about how exactly, right? Whether we want to use a 1 volt or 2 volt, how do we move the electrons? No, so that's not really something that we are going to cover in this course. Okay? And that's actually, so if you look at these, right, these bottom layers, right, physics, devices, and circuits. So this actually belongs to more of the traditional electrical engineering courses or EE courses. And many of you have already, like I mentioned, right, so some experience, right, most likely with some programming languages, and you might have already written up some applications using those programming languages. So this is where if you look at these 3 layers of stack, so this is where the traditional CS, right, related materials belong to. And CE, right, so we talk about ECE, we talk about CE, right? CE really is the computer engineering. So this is really about the sort of hardware software interface. This is the stack, right? The middle of the stack. So these are the layers between the software stack and the traditional, right, physics, right, and devices. Okay, hopefully this makes sense, right? And we're going to start with one extremely important abstraction. Okay, this is so-called digital abstraction. Okay, and later on, we are going to talk about another extremely important abstraction. It's called ISA, or instruction set architecture. Okay. So these are really the 2 of the essential concepts in this course, right? Okay, so again, computer engineering, right, is really about the sort of interface, right, between the the traditional EE and the traditional CS, right? So hardware software interface. So let's just start with this digital abstraction. Right? What exactly is a digital system? Right? Actually, the definition is extremely simple. So anything that has finite number of values, that's a digital system. As simple as that. Right? So is English alphabet a digital system? Yes, right? How about the dictionary? Is it digital? Yes, right? It's not infinite, right? It's finite. And the simplest kind of digital system is something that we want to study, right, in this course. It's called a binary system. This is where we only use two states, right? So the simplest form is just 0, 1. We only have two states. So nice thing about this is, it's very simple, very efficient, right? And this is something that we can, build in a low-cost way, right? So one more time, the basic unit of information in this system is just 0, 1. We usually call them binary digit. Okay, the shorthand or short form is bit. Okay, I'm sure many of you have heard about this notion, right? Bit. A single bit is just a single state, right? 0, 1. You have two values. And again, we are using electronics devices, right? So that's where we do need to rely on these electrical properties, right? So usually we use a voltage, okay, to represent these two states. So usually the high voltage means a 1, and the low voltage means a 0. Okay? In this case, I'm using 2 volt, right, to indicate the 1, and 0 volt to indicate 0. So in some of the more modern chips, right, the actual voltage to represent the 1 might be slightly lower. Okay, so you guys may sort of wonder, right? So how useful is this thing, right? It's so simple, right? Sort of shocking simple, right? The nice thing is later on we are going to find out there are actually many nice advantages about the system. So we can actually build very efficient circuits, so which is cheap, which is small and fast and low power. Okay, we'll touch on some of these aspects, right? Compared to other systems like a decimal system that you guys are familiar with. And also, I want to really convince you guys that it's actually a good idea, right? So the reason that we use just 0, 1s is that in many cases, we don't have to rely on perfect electronic circuits, right? So I just mentioned that we use 2 volt, right, to represent a 1. But the nice thing is that actually we don't have to exactly use 2 volt, right? Otherwise, the device we use, it may age, right? It may get older, right? So then the 2 volt may become 1.99, right? The 2 volt may become 1.75. Okay. The nice thing about digital system, we can actually tolerate some noise. For example, in this case, anything between 2 volt and 1.5 volt is still a 1. Okay. So same thing, right? Same thing for the 0. Okay, we can have a nice noise margin here. I really recommend you guys check out. There's actually a section in the book, right, that talks about the noise margin for this digital system. That's a very useful read. So basically, with this system, right, we don't have to make it perfect, right? We are robust to noise, and like I mentioned, it's cheap to build. It's very efficient. And I also actually want to turn this into a sort of live challenge, right, to you guys. Just want to make sure that I convince you guys that this is indeed something very useful, very ubiquitous, right? That even though we only have 0, 1, right? In fact, I believe that you can find such binary encoding just around you. Right? Can you guys just look around your room and name one thing that can be encoded using binary digit? Okay, so right, very good. You guys are questions are coming in really fast. Okay, switch, right? Okay, many of you are saying that switch, right? Very good. We're actually going to be talking about switch in the next lecture. Light switch, lamp, that's also switch, I suppose, right? Right, pen, open or close. Very good. So fan, I guess you are also talking about switch, right? Light, microwave. window close or open, that's also state, right? That's basically also a switch. Doors, keyboard press, very good, right? Whether the keyboard is pressed or not. Attendance, what about attendance? Alma, can you elaborate?
I just meant like if someone's present or not present, it could be 0 or 1.
Excellent, right? Again, this is a state, right? So basically we are looking at state, also a different state, right? Again, switch, okay. Blinds, right? Whether it's shut or open. Okay, fridge. What about fridge, Max?
A fridge, could be like to turn on like the freon in the back to make it cold or to turn it off. Not really sure how it would work.
Right, sure. There are also all sorts of states, right, in the fridge, right? Window, mentioned that again. Any key on my ceiling fan. Okay, right. It's also about, right, whether it's a lock, door, okay, phone charger. Emily, what do you mean by phone charger?
I meant like whether the device is plugged in or not would be like 0 and 1.
Okay, great. Okay. Mitchell says sock. Okay, what about sock, Mitchell?
So the sock is either on my foot or the sock is off my foot.
Okay, right, very good. Light state, right? So pretty much most of these are about states, right? Shutter, right? Okay, very good. Okay, trash bin, Taylor. You mean whether it's open or not? Trash bin?
Yeah, sure. Yeah.
Okay.
So like when someone's close to the trash bin, it can be open, and like when someone get away from it, it close again.
Right. Okay. Power dry or wet? Very good. Okay. Ambrose saying awake or asleep. Right. Very good. Okay. Phone off or not. All right. Great. So coffee mug, fuel not empty. Wow. And there's so many interesting ideas. Right. Oh yeah. Steve, make a very good point. Right. So Steve Hong is saying that SU causes. Right. Very good point. All right. So let's see. Actually, I also found something in my room. Okay, let me show that to you. And I need to switch my screen a bit. I found this thing, okay, in my room. This is actually a heater, right? This is something that I use a lot, right? You guys are seeing this video, right? Okay. Right, so this is basically the first switch, right? So whether this will be to high power, low power, right? So this is something that you guys already mentioned. I want to make sure that although this looks very simple, right, very intuitive, right? Actually, we can build amazing things with the switches. We're gonna quickly find out very soon, right? And basically any button, right? So the stage, right? So you guys mentioned many of this, right? So essentially it's about whether this is switched on or switched off, right? But let's look at something over here. Okay, so there's actually a timer as well. Okay. Any guess? How long can I time this thing? There's actually also LED. Let's play this a bit. Right. So if you push the button, so this light will be on soon. Right. This means 1 hour. Then many of you may think that we can time it up to 4 hours, right? But actually, this heater is slightly more sophisticated than that. Let's see. Okay, when I press it one more time, of course, right, 2 hours, right? So let me press it one more time. What does this mean? 2 lights are on, right? So this means 3, right? Very good. 3 hours, okay? I hope you guys now see what I'm going with this, right? Okay. Next, 3, of course, 4, right? And this actually means a 5, right? 5 hours, and we can go to 6, then 7, right? We can time this thing up to 7 hours. All right, any questions about this? right? You know, some of you guess 3 hours, right? Okay. Okay, if you understand this, actually, you know, you guys pretty much understand how binary system, how binary numbers work. As simple as this. Let me come back. Here my slides. Okay. Right, you know, I just showed you this thing, right? Okay. You look at, remember the video, right? So there's a high power, low power. That's 1 bit, right? But 1 bit can only represent up to 2 values, right? So what if you want to represent more than 2 values? So that's where we are looking. That's why we look at the timer thing, right? So there, that one has 3 bits. Right? Okay, so to represent more than 2 values, we just have to use more than 1 bits. As simple as that, right? But if you use 2 bits, we get 4 possible values, right? 0, 0, 0, 1, 1, 0, 1, 1. Okay, just imagine this as the light switch, right? The LED light that I just showed you. Okay, and what does 1, 1 mean, right? If you just treat it as a decimal number, any guess? It's a 3, right? So remember that heater thing, right? When press the button twice, right? 1 hour light came on, then the 2 hour light came on. We add them up, right? It's a 3. And the heater, right, actually has 3 bits, right? So 3, 1 hour, 2 hour, 4 hour. So that's where we can actually encode up to 8 states from 0 to 7. Okay, in this case, 111 really means a 7. Okay, as simple as this. Okay, if you're new to binary system, right? So don't be scared, right? It just works like that heater thing. Okay, and if you have n bits, right? So we can encode up to the n possible values, right? Okay, in fact, this is just very much the same, right? So with the decimal system that we are used to, right? If you look at this number, right, 3 to 9. So really, we are using this so-called positional number system, right? So where we assign a so-called place value or weight per digit, right? So over here, so for this given bit, right, the rightmost bit, we are assigning, right, 1, right? The weight is 1 here, 10 to the 0. Okay, and then the second one is 10, right? The third one is 10 to the 2, right? 100. So that's actually how we, you know, parse a decimal number. For binary number, it's just the same, right? So the only difference is that we are using a different space, right? We are no longer using a base 10 system. We are using a base 2 system, as simple as that, right? And again, so if you look at this, there's actually another live challenge. Let me go back. I meant to press the, okay, this one. Okay, so again, think about the heater, right? The first digit has a weight of 1, right? 1 hour. Second one, 2. Third one is 4, right? To the power of 2. So that's how we parse a binary number, a binary string. Okay, let's see. Any questions here? Okay, all right. Okay, great. Then you've got the answer right, right? 3. Okay, so basically this one adds up to a 5. Okay, so hopefully this makes sense, right? I just want to make sure that you guys already got the key idea, right? Let's just do another live challenge. Okay, can you guys go to this website again? I need to stop sharing and share. Sorry. Go to this website. I need to start the. Okay, so this is actually a board game. Okay, hope you guys are seeing the screen, right? So we can go to this item pool website, right? This is actually a board game that we played in the past, right? So which is supposed to be useful for testing my memory. Okay, but you guys don't need to worry too much about, you know, what's going on with this different mode, right? But just look at this board, right? So we have 4 rows. Okay, we have not yellow, black stone and white stone. So I'm asking you guys to convert the first row into a decimal number, right? Each black stone indicates a 1. Okay, each Y stone indicates a 0. Okay, I already gave you the answers, right, for the rest of the rows. Okay, see the answers are rolling in, right? Many of you are agreeing with each other. Okay, but we do have many different opinions, right? Which is good. Any questions about this exercise? Again, this is not a quiz. This is just in-class exercise. I'll give you guys maybe 10 more seconds. Okay, so feel free to continue to answer, right? Enter your answer, right, in this on this website. Let's see what's the answer. Okay. All right. Okay, so indeed, right? So it's great, right? It's great to see that most of you got it right, right? It's 13, right? Looks like some of you got a little bit confused by the question, right? Which is fine, right? That's why we are doing this exercise, right? So later on, if you were not clear about the question, just ask me. Okay, you can directly unmute yourself and ask. Right? Again, what we are trying to do is we are not converting that to a binary number, right? Some of you did it right, which is good. But we actually want you guys to further convert this number, right? This binary string into a decimal number, right? The correct answer is actually 13, and some of you are very close, right? 11, 12. Right? Okay, looks like for some of you, you probably got this in the opposite way, right? So over here, a black one means a 1. Okay, again, I need to come back to my other screen. Okay, right. So like I mentioned, the correct answer is 13, right? We have four stones, right? 3 black stones, right? The first one, let's just read this, right? So in case you're still confused, right? The first one has a place value or weight of 1, right? The first black stone. Y stone means 0, right? One thing is, regardless of the position of the Y stone, right? If a Y stone in that position, you have a 0. Okay. And for the second, right, or this guy, right, this black stone, right, it means a 4. The last one, the leftmost one, so this means 8, right? 8 is 2 to the power of, right, 2 to the 3. Okay, is it clear? Okay, I think there's a question. Okay, Steve's asking, and just confirm this one will be 4 bits. Yes, correct. This is a 4-bit, right? This is a 4-bit. Okay. All right, very good to see that most of you got it right. Okay, we just look at how to represent the bits, right? So how to represent the information, binary information using bits. So now let's quickly look at how we actually compute on them, how to process them. So there's something called logic gates. So these are some of the compute primitives that we're going to use a lot in this course. Okay, let me just quickly introduce some of the simple ones. Okay, so you can just consider these gates, right, logic gates, as functions, right? These are so-called the Boolean functions. We're going to talk about Boolean algebra in the next lecture. These functions or these gates process input, right, binary input, and produce binary output. Okay, in this case, if you look at this one, so we have something called NOT gate. Right? It's actually also called inverter. So this is a 1 input, right? The input is A, and 1 output function. And these are the symbols that we usually use. We can either use not A or A bar or A prime. Okay. So in the rest of the course, in most of the homework and also exams, for the sake of simplicity, so we are going to be using A prime. So what exactly does this thing do, right? This NOT gate. Why is it called inverter? So basically, it's basically inverting the input. Okay? And the way that we define a logic gate is by using the so-called true stable. Okay, so this is the term true stable, right? So we basically put the input right on the left and the output on the right. We enumerate. So this is important. We want to enumerate all possible input values in this truth table. Each row means a possible input value. Since this is single input, right? Of course, we only have 2 rows, right? 2 to the 1. Okay, so you have 2 inputs. We will have how many rows? 4 rows, right? And in this case, for the inverter, right, what it does is it's basically inverse the input. If you input 0, the output is 1. If input 1, the output is 0. Okay, as simple as this. That's why it's called inverter. And we usually call it either inverter or NOT gate. And the second one is called AND gate. Okay, this is actually a 2-input function, 2 input, 1 output function. And the symbol we usually use is we can either use, right? So this is the how we draw it. This is a symbol. And the notation-wise, we usually use A times B, okay, or dot A dot B. So this is the simplest kind of a notation. So you're gonna find out why. Okay. So the definition of the AND gate is, if we only the output side on the output side, Y is 1, if and only if both A and B are 1s. Okay, so that's the definition of the AND gate. Is it clear? Right? If you look at the truth table, right, it's basically agreeing with the definition, right? Okay, if A, B, they are both zeros. Okay, we have of course 0 and 0, 1. Okay, only one, only single one, 0. Again, here only single one, we have 0. Only both A and B are 1s. So the output is a 1. Right, so this is AND gate. Hopefully this notation also makes sense now, right? You can just treat it as sort of a multiply, right? This is really A multiplied B, right? You treat this as sort of decimal numbers, right? So look at A, 1 times 1 is 1, right? And 1 times 0 is 0. Okay, so that's why people are using this notation. Of course, we are using a binary system now. And the third gate that we're going to use a lot is called OR gate. So this is where the output is 1 if one of the at least one of the inputs is a 1. That's where we have OR gate. And the truth table is like this, right? So this is where we have a lot more 1s in the output column. We're going to use this term a lot, right? So this is the output column. Okay, so this is the column right to the right of this vertical bar. And these ones are the input rows, right? So each row is an input row. Each row corresponds to an input combination. In this OR gate, right, we only have a 0 when both A and B's are zeros. That's it. And we usually use this notation, plus. Okay, we use A plus B to indicate the OR gate. Okay, hopefully this is simple enough, right? Any questions? Krisha is asking, would it be right to think of 1 as true and 0 as false? Yes, right. So that's a very good intuition. Okay. All right. So once we know this case, right, I just want to make sure that I give you some concrete ideas of what I mean by abstractions. We can actually use this case to build up more complex building blocks, right? Like this one. This is actually a 1-bit adder. We will have a dedicated lecture on addition, so you guys don't need to worry too much about what's going on in the circuit diagram, right? Some of the gates are already familiar, right? So this guy is an OR gate, right? And this is the AND gate, right? And this thing, so this is something that we'll introduce in a later lecture. It's called the XOR, or exclusive OR gate. It can be decomposed into inverter, AND gate, and OR gate. And this is a truth table for the XOR. For now, you guys don't need to worry too much about this. But I want to quickly show you the truth table of this 1-bit adder. Okay, just want to convince you guys that this is indeed doing some addition. Okay, so in this case, we actually have a 2-bit output function. Right? If you look at this truth table, okay, we have 3 input bits A, B, C sub in. Again, don't worry about the notation here. This means carry in. We're going to talk about carry in a later lecture. And for the output columns, we have two output columns. One is called C out. This is called carry out. The other one is sum. Okay, this is a sum bit. Okay, right. Again, just don't be too worried about the notations here. I want to quickly convince you that this is indeed doing additions by just looking at the truth table, right? So we have three inputs, right, over here, A, B, C in. Let's just add up these three values, okay, and see what is the corresponding output. But of course, if you just add the 3 zeros, we get a 0, right, on the opposite side. This is not surprising, right? We add up 0, 0, and 1, we get a 1, right? Just read this two, right? Just read out these 2 bits and then convert it into a decimal number. What is this? This is a 1, right? Same thing here, right? How about this one? A is 0, B is 1, C in is 1. We add them up. We are supposed to get a 2, right? You look at this row. And this one, the corresponding output is indeed a 2. If we convert this 2-bit string, right? This 2-bit value into a decimal number, right? And let's look at the last one. Maybe this one is more interesting. 1, 1, 1, right? We add them up, we get a 3, right? And indeed, we have a 3. Okay, right? So if you just look at this truth table, it's actually powerful enough, right, to represent any kind of function. So we just have to allocate more bits, right, for the input columns and output columns. Make sense? Okay. All right. Okay. I think we're almost done, right? If you look at this abstraction again, so we just talked about gates, right? We use it to build a 1-bit adder. We can actually further abstract away, right, certain low-level details. You can just abstract this whole 1-bit adder as a black box, okay, like this. And soon you guys will find out how do we actually use this black box to build even more complex multi-bit adders. Okay, we just show you how to do a 3-bit additions, right? We can actually do up to however number of bits that we want, right? In this case, we are doing an addition for 16 bits. Okay, and this is where we get the sum bits, right? And this is why we have something called carry, right? See, you can see that it's indeed being carried through many 1-bit adders. Okay, so that's why we call it abstraction, right? And in many cases later on in the course, in the homework, I may not ask you guys to draw this thing, right? When we build something more complex, I may not ask you to decompose everything into AND gate or OR gate. I may just ask you to, can you give me the 1-bit adder? Just use the 1-bit adder as a building block. Can then build something more complex? And once we have this, okay, we can build even more complex things. Okay, and see here, so we further abstract away the adder, then we just create another box, we call it adder. That's it. And then you guys will learn what it is pretty soon. That is actually a multiplexer. Okay, you'll know this in a few lectures, and different kind of memories like data RAM and DRAMs or SRAMs. Okay. And this is actually a microprocessor. This is actually something that you guys will be building for your last lab. Okay, so this is the thing that you guys will build on the FPGA. All right, so okay, this is really about abstraction, right? Yes, okay, so to be very close, make sure you're right. So once you finish this course, right, you will know many things that the Intel guys, right, they are indeed actually using many of this fundamental concept to build the Intel processor. All right, so this is the course roadmap, really, right? We started out with building this very simple gate, right? And then we started out, and then from this single gate, we build something slightly more complex called convolutional logic, right? The logic building blocks. Then we build something even more complex, right? We put them together to build a whole chip. And actually in this chip, right? So there are memory systems, right? The processors, right? You guys will find out there are also buses. So that's something that we'll cover at the end of the course. Okay. All right. Any questions? This is pretty much the course overview. If not, okay, right, so this is what we are going to build, and this is pretty much the end of the first lecture. Okay. And please make sure that you guys read the syllabus, right? And also these are the book chapters to read before the next session. All right. Okay. If there are no more questions, let's stop it there. Thanks, guys. I'll see you guys on Thursday. Bye.
Thank you.
Bye. Thank you.
Thank you.
Thank you.
Thank you.
Thank you.